In this video, we will explore the differences between JFETs and MOSFETs. Sometimes we need to take a step back and explain the basics. A JFET, or junction field effect transistor, is a simple yet powerful device. Think of it like a water hose. When it's wide open, current flows freely. By applying a gate voltage, it's like crimping that hose, controlling the flow of electrons with precision. The primary role of a JFET is to amplify tiny signals without adding electrical noise. That's why you'll find them inside every high-end microphone. The clarity and detail of the sound simply can't be matched by other transistor types. Despite being a mature technology, JFETs are far from obsolete. In fact, demand is rising again. Take sonobuoys, for example. These underwater acoustic sensors rely on JFETs because of their unique combination of low noise, high input impedance, and rugged reliability. Unfortunately, many engineering programs barely touch on JFETs today, leading to the misconception that they're outdated. But the reality is different. JFETs offer advantages no MOSFET or BJT can replicate. Exceptionally low noise for sensitive signal detection, very high input impedance, preserving weak signals, and strong performance in harsh conditions, including radiation-heavy environments. So when we say JFETs are alive and well, we mean it. In many applications, they remain the best tool for the job. When engineers first encounter our technology, one of the most common questions we hear is, why JFETs? Why not just use MOSFETs? The short answer is that JFETs and MOSFETs are related, but they're not interchangeable. Most designers are familiar with MOSFETs because they dominate the digital and power electronics world. JFETs, by contrast, occupy a very specific niche, handling the smallest, most delicate signals with the least possible noise. That's the purpose of this slide, not to suggest that one device is universally better, but to remind designers that JFETs provide a unique set of advantages. Later slides will dive deeper into those differences, especially around noise, impedance, and stability. So think of this as a marker. If you know MOSFETs, then you already understand the basic family tree. But if you're working in high-end analog, measurement, or sensing, the JFET may be the missing piece you didn't realize you needed. Most designers default to MOSFETs because they're ubiquitous in digital and power electronics. This slide is a quick reset. JFETs and MOSFETs are related, but they solve different problems. When the job is to handle very small, delicate signals, think precision sensors, microphones, sonar front ends, the JFET often wins. Why? Because it delivers exceptionally low noise and very high input impedance, preserving weak signals instead of loading them down. JFET gates are reverse bias and draw essentially no input current, which cuts current-related noise at the source. Beyond noise, JFETs tend to be robust at the front end. Higher ESD tolerance at the gate compared to many MOSFET inputs. Radiation resilience, thanks in part to the absence of a thin gate oxide that can trap charge. Stable performance over temperature with simple, predictable biasing. Low gate leakage, which matters when you're measuring picoampere level signals. So, if your design lives at the intersection of tiny signals plus harsh environments, a JFET front end can simplify the entire signal chain. Fewer workarounds, cleaner results. We'll explore specifics in the architecture slide next. Here's how a depletion mode JFET actually behaves. The water hose analogy is useful. The channel is naturally open, current can flow, and the gate pinches that channel down as you apply reverse bias. When VDS equals 0 and VGS equals 0, the channel wide open, with no drain source voltage and no reverse bias at the gate, the depletion region is minimal. The channel is at its maximum conductivity. If you were to increase VDS from here, current would immediately flow because the device is normally on. In region B, where VDS is greater than 0 and VGS is negative 6 volts, or in the pinch-off region control, applying a negative gate-to-source voltage expands the depletion region into the channel. As VGS approaches the device's VGS off, the channel narrows dramatically. At pinch-off, it effectively closes and the drain current falls towards 0. This is how a JFET controls current, by shaping the channel with an electric field, not by injecting base current as BJTs do. The result is precise control with very low input noise. In C, where VDS is greater than 0, VGS is 0, which is an unbiased gate, conduction set by the device geometry. With the gate at 0 volts and a positive drain to source voltage, the device conducts at or near its IDSS, the saturation current at VGS equals 0. The specific current depends on the geometry, which sets transconductance, capacitances, and noise, and on the operating temperature. Designers bias around this point to trade off gain, bandwidth, and noise by their application. The key takeaway, a JFET is a voltage-controlled and normally on device. By reverse biasing the gate, you crimp the hose to set the exact current you want, cleanly and quietly. This physics is why JFETs excel in low-noise front ends and high-impedance sensing. One of the biggest advantages JFETs bring to the table is their inherent low-noise performance. To appreciate this, let's compare them briefly to bipolar transistors. Bipolars rely on current injection at the base, which introduces a level of shot noise that can never fully be eliminated. JFETs, on the other hand, use a voltage-controlled gate with almost no input current. That's the key. It's this physics that allows JFETs to handle the tiniest signals without burying them in unwanted noise. In practical terms, that means a JFET can amplify signals from a sensitive microphone, a medical sensor, or a military sonar system while maintaining a clean and faithful representation of the original signal. This isn't just theory. Devices like our IF3601 are recognized as some of the lowest noise transistors in the industry. That's why designers who care about ultra-quiet performance, whether in a recording studio or a submarine, still rely on JFETs as their go-to device. If you enjoyed this video, give it a thumbs up and subscribe for more expert insights into JFETs, analog design, and low-power electronics. Hit the bell icon so you never miss an update from InterFET. Got questions or ideas for future videos? Drop them in the comments. We'd love to hear from you. Interested in using JFETs in your next project? Reach out to us directly through our website or the link in the description to speak with our team of experts. Stay connected, stay curious, and keep innovating with InterFET.